graph theory. Homework 10 is to be turned in at EB2 3222, slotted under the door. I'm going to go very quickly. Today we're going to talk about graph theory. A graph is a set of nodes and edges. A directed graph is one where the edges have a direction, so they start at one node and end at the other, just like we did for binary relations. And an undirected graph doesn't have any arrows on it, and that will work for symmetric relations. So these circles are nodes, and the arrows or lines in between are edges. So what do we use graphs for? We use them for abstractions, for solving problems where we only care about how things are connected. So one example is when we deliver postal mail, and nodes are fixed locations like houses or businesses, and I'm drawing an arrow in between them if these are adjacent houses or businesses, and then we want to figure out if we can deliver mail to everyone. And in this case, all these adjacent addresses, we can deliver mail to all of them by going to all the nodes exactly once each, but not using an edge more than once. So in this graph, we can start and end at different places. For example, we can go AD, DG, GH, HE, EB, and BC, C to F, and F to I. There's three different ways of writing out edges. Is F to I with a bar over the top, Fi with brackets around it, and Fi with parentheses around it. So we can actually write out a path with putting the sequences of nodes that we visit. So A and I are different starting and ending places. So we could deliver the mail, but we can't actually get back to where we started without reusing an edge in this graph. So a Hamilton path is one where we visit all the nodes using no edge more than once. And a Hamilton cycle, though, is one where we actually need to have the start and the end equal to each other. The Hamilton cycles problem is an NP-hard problem, and an NP-hard problem is one where you can check a possible solution in polynomial time, meaning that it's pretty fast to check whether the solution is a valid one, but you can't guarantee that you can find a solution in polynomial time. And that means that given the number of nodes, there's no polynomial that will tell me a running time that is enough for me to actually check all the possible ways that we could have Hamilton cycles. So the only known guaranteed solution for Hamilton cycles is to list all possible orderings of all the nodes, and there are n factorial ways to do that, and that is never bounded by a polynomial, as we learned in the Big O section of the class. So there's one, even though it's not computable in a polynomial amount of time, whether a graph has a Hamilton cycle or not, there are a few properties that we can look at to see whether or not there's a Hamilton cycle. One is that when we have degree 2 nodes in our graph, the adjacent edges actually have to be included in the Hamilton cycle, because in a Hamilton cycle we have to get to every node and we have to get away from every node. That means we have to have an entrance and an exit edge from every node, and they have to be different. So if we have degree 2 nodes, then the adjacent edges actually have to be included in the Hamilton cycle. If we mark all of the nodes where a node has degree 2, and then mark all the edges adjacent to them that must be included in the Hamilton cycle, if we can find a subcycle within that, like this ABE HGD cycle going back to A, then we actually have a subcycle in there, and that means we can't have a Hamilton cycle because we are not allowed to get to any node and get back to it and then leave it again. And that's what we would have to do to visit all these required nodes for this particular Hamilton cycle. Here's a few other pictures of graphs. Anything that looks like a bow tie we can't do, because this node B, we're not allowed to say start there, come back to it, and go back out again. So all these degree 2 nodes require that we actually visit all the edges, but B will be visited too many times that way. We do have a Hamilton path, though, starting at D, go to A, go to B, go to E, go to C. If we have any lonely nodes sticking out that have degree 1, we can't have a Hamilton cycle, although in this graph, again, we have a Hamilton path where we start and end at different places. Here's another sample graph that does have a Hamilton cycle. So, for example, we can start from A, go to B, H, G, E, F, D, C, A. And with these, we just have to check them by by hand and see if we can find a solution. Euler circuits, on the other hand, we can always actually do this in polynomial time. So an Euler circuit is one that starts and ends at the same place and uses all of the edges in the graph exactly once each. And the question that we need to ask to figure out if a graph has an Euler circuit is, do all of the nodes have even degree? Right, so one explanation is if we have a node that has odd degree, then it either has more entrances or exits than it has the opposite. So that means that I'm going to get stuck there at some point. So if anything has odd degree, I don't have a way to get back out once I get back there. So odd degree nodes means that you eventually get stuck. So let's just draw a little picture of that. So if I have a degree 3 node, then no matter what happens, if I get there and I leave, then somehow if I get back there, then I'm stuck there. I can't leave again because I'm only supposed to use each edge one time. And I've already used all of the edges adjacent to that, and now I'm stuck there and I can't leave. So we can't have any odd degree nodes, otherwise we'll get stuck. There's one special kind of Euler path. It is okay to have exactly 2 odd degree nodes, and then you can have an Euler path that starts and ends at different places. So just like Hamilton paths, we can have Euler paths. So an Euler path exists in a graph that has exactly 2 nodes with odd degree. Now there's an algorithm called Kruskal's algorithm that we use to find Euler paths, and it's really, really easy. So let's actually use one of our graphs again. Okay, so this graph is not good because it has lots of degree 3 nodes, so I got to fix that. There we go. By the way, this crossing right here does not have a node. It's just 2 paths crossing because there's not another way to do it without crossing anything. And if you're interested in this kind of thing, there's a whole field of mathematics and computer science called graph theory, and they look at things like planar graphs. So planar graph is one that can be drawn with no edge crossings. And this one is not a planar graph. There's one edge that we can't rearrange the nodes so that we can get them not to cross. Okay, so we just have to start somewhere. It's not precise. It doesn't have to be precise. Just have to start somewhere. Let's say A. Pick an edge. Any edge that leaves from A and goes somewhere. Let's pick B. Pick another edge. You just do that. Pick edges that you haven't used until there aren't any left. Unless you get stuck. So getting stuck means I pick the last edge that gets somewhere and I can't get back out to the rest of my graph. So if you get stuck, backtrack 1 and then back out. So I'll just pick from B to H and then back from H to B. And I only have one choice. Now I'm going to go to D. Let's go to E. Let's go to F. Go to C. Go to D. Go to F. I don't have any other choices. I have to go to H. And once at H, I don't have any other choices. I have to go to G. Now I have a couple of choices. It still doesn't matter where I go. Let's go to E. E only has one choice. I have to go to C. Once I'm at C, only one choice goes to A. And then once I'm there, I have to go to G. And then I can go back to A. It is literally that easy. You just pick edges. If you get stuck somewhere and you still have some nodes you haven't been to, then go back a step. So what does a dead end mean? It means I've used all the nodes. Like once I go there, there's no way to get back out from it. So if it is a dead end, you just back up a step. If it's a dead end, try again. So if you are asked for an Euler circuit or an Euler path, you should be able to do it very easily. So E is for easy, for Euler, for edges. H is for hard, for Hamilton. It needs to visit all the nodes. Any questions on this? Okay. You know what? I told you the wrong name for this. This is Fleury's algorithm. We're going to do Kruskal's algorithm next. Sorry about that. That's Fleury's algorithm. I'm sorry about that. So the next thing we're going to do is what's called a minimum spanning tree. So we have to know a few things before we know what a minimum spanning tree is. A tree is a graph with no cycles. And we drew some trees when we were talking about counting, right? We drew trees for like choices that we were making, and the nodes in those trees were representing times when I were making a decision, and then the edges were different. They went to different decision points according to what choices I made. So those are trees. They don't have cycles because none of the choices, I didn't go back to any of them from where I was. So a tree is a graph with no cycles. And what do you think spanning means? Any guesses? Okay, so all the nodes. And what else might we need? Do we need any edges at all? We need the minimal number of edges so all the nodes are connected. So spanning means it has all the nodes, and they're all connected with edges. But minimum means I can't have any fewer edges than I have. Okay, so lots of graphs have repeated edges. So you might have thought it was weird that I drew these double edges on this graph, but it's actually pretty normal. So a lot of times we use graphs to represent things like networks of computers, and there's way more than one connection in between lots of pairs of computers. Because why? Because why? Well, we have more than one port, but also we want redundancy. So we don't want to be left out in the cold on the internet. So we have lots of connections as backups. That's like if you're doing your discrete math homework, you don't have just one friend you can call. You have a lot of friends so that when you need that help, you can find someone who can help you with the problem so you don't get stuck. Okay? So we need to have redundancy in graphs if we want them to stay connected, even if some of the edges might go down sometimes. Okay, so there's actually an algorithm called Kruskal's, no surprise there. It's an algorithm that's really simple to find minimum spanning trees. And by the way, we also will try to do them with a minimum cost. So with each edge, we can also have associated with it a cost. Like, for example, if your edges were representing roads, you could, and they were toll roads, you could have a cost for going on that road. Or you could have a distance of that road. So I might actually have multiple roads connecting different places, but one of them might be longer than another one. So that cost would be proportional to the distance. So we can use numbers to represent some kind of cost or distance in between edges. In between nodes. So let's just make an example, then do Kruskal's real quick so we can see what it looks like. Okay, so next to every edge I have given a cost. That is 1 through 5. Kruskal's algorithm is as simple as Fleury's algorithm. So what we're going to do is we're going to include all the nodes. So we'll just go ahead and write them all down because we have to. And then we're going to find the cheapest edge that connects any pair of things, and we're going to add it to our graph. So, give me an example of a cheapest edge. Cheapest being the cost, that's the weight. A to G is one of them. It doesn't matter which one you add, by the way. It does not matter which one you add. So A to G is the first one we're going to do. Okay? What's the next cheapest? B to D, E to I. There's no more ones, right? So now I can look at the twos. And which one did you suggest? I didn't put a cost on here. Let's put a cost on that one. AD, I don't have a cost on there. Wow, I just messing up left and right. Let's put another one on there. BH, EH, thank you. Let's put another one since we're not done with the ones. So we can put E to H on there. So we're going to do this as long as we don't make any cycles. So we're going to add the cheapest one that's left in the graph, and as long as we don't make a cycle. So now we're going to consider cost 2 edges because we've already done them. We've already done all the ones. So let's do B to F. That's a 2, and we still haven't made any cycles yet. Okay, so we can do F to I. It doesn't matter where we are. We can put them anywhere, so we don't have to be at like the I node or anything. So there's another 2 over here. Still haven't made any cycles. What about this one? What about E to F? That'll make a cycle, so I cannot add it. Okay? And the only thing we haven't got connected right now is C. So we need to find one of C's adjacent edges that'll get it connected, and that is of minimal cost. So what's the minimum cost to get to C? 3. So either one of those will work. So I can either do C to F, my loopy one, or I can do B to C. Doesn't matter which one because it will end up being the same cost. So the interesting thing with Kruskals is it doesn't matter if you're choosing between edges that have equal weights. You will end up with the same cost, minimum spanning tree. So the cost is the sum of the cost of connecting all these. So let's add that up. 1 plus 2 plus 1 plus 3 plus 2 plus 2 plus 1 plus 1. So the reason why we have minimum spanning trees and we calculate this minimum cost is that it's just one way of calculating the cheapest way to get all the nodes connected. Yes? The cost is the sum of all the minimum weight edges. The costs are given always. So that's usually inherent in your network. So your network normally has some kind of a cost associated with getting from one node to another one. So like maybe these are, actually we use this for like gas lines. If you're sending gas over a pipeline, it'll have some cost associated with it that you have to pay the owners of the gas line or anything like that. So we have that for everything. So one of the things you'll need to be able to do is actually find a minimum spanning tree. But as you can see, both Fleury's and Kruskal's algorithms are relatively easy, and they will always work. They're guaranteed. Someone else has done the work of proving that they always work, and they always give you, Kruskals always gives you the same minimum weight, no matter which edges you pick, as long as they are the smallest ones, one of the smallest ones left. Any questions? So when might we be interested in a minimum spanning tree, what the cost is? In pathfinding? So this would actually give me a cheap way to get between any pair of nodes. Maybe not the cheapest. There might be a cheaper, more direct way, but this is the cheapest way so that all the nodes can get connected to all the other nodes. And that would be important in a network where you actually want to be able to communicate with all the nodes, even if it takes some degree of latency. Yes? Traveling salesman using public transportation, yes. Except we don't get back home with this usually because it's not a cycle. He gets stuck out. It's the nomadic traveling salesman, yes. homeless traveling salesman. Yeah, so you might also, if you were considering different subway layouts, you might actually pick a minimum spanning tree. That's a really great example. You might pick a minimum spanning tree to actually implement, right? So if you were considering possible layouts and then you had the cost for all of the different connections, then you'd pick a minimum spanning tree because we're not going to have redundancy. That's what buses are for, right? So we would do the subway with the minimum cost and then add buses on top for redundancy. Very good example. So today is jam-packed with definitions, so we're going to move on to another one. You'll need to practice a few of these problems, but your homework will give you some practice on them. The fourth section of the final will be on everything that we're doing for the next few days, and the same stuff that's on homework 10. So the final will have 3 bigger sections that correspond to each of the tests and a 4th section corresponding to the homework 10 material. Okay, so the next thing we have to do is Hasse diagrams, and you've already seen a little bit of this when you did your binary relations tutorial on Novanet. So Hasse diagrams are graphical representations for binary relations. And what kind of binary relations are they? Do you remember? Partially ordered sets. I will repeat it. So a partially ordered set is a relation that is reflexive, antisymmetric, and transitive. So it has to have all three of those properties. And a Hasse diagram is a directed graph for a binary relation. That's a partially ordered set, but we don't draw any of the reflexive edges and we don't draw any of the transitive edges because we already know that it's reflexive and transitive, so we're not actually going to draw all that because it makes it a hairy diagram. So if I give you a relation, then I want you to be able to draw the Hasse diagram for it. So one of the ways you can do that is just by drawing the directed graph and then rearranging it until all the arrows go up. So that's the other thing, is that since it's antisymmetric, I know that there's no cycles. So there's no things don't go in two directions, so everything goes in one direction. So for a Hasse diagram, I make all the relations actually go up, and then I don't have to have any arrows. Okay, so let's make a sample partially ordered set. Okay, so first of all, we're going to cross out the reflexive edges because we know we don't draw those. And we have 1 to 2 and 2 to 3, so that means we have to have 1, 3 in there for transitive. And we have 1 to 3 and 3 to 2, so I have to have 1 to 2, so I have that. I have 2 to 3 and 3 to 2, I have 2 to 2, that's fine. And that is transitive. So I have a reflexive, antisymmetric, and transitive relation. It's antisymmetric because I can't have that one to make it antisymmetric. Let's see, 1 to 2, and 2 to 3, 1 to 3. Okay, so that's actually deleted from the set. Sorry about that. So the ones that are crossed out are ones we're just not going to draw. So we have 1 to 2, 2 to 3, and 1 to 3. So our challenge is to write down the nodes that, the node that goes at the bottom that doesn't have anything that goes to it. Is there any number here, 1, 2, or 3, that doesn't have anything going to it? 1. So I can draw 1 on the bottom. And then the next level has to have stuff that only 1 goes to, but nothing else. So 2's there. And 1 goes to 3, but 2 goes to 3. So 3 can't be on the same level as 2 because it has to have an up arrow between 2 and 3. So there we have our edges. We didn't need the 1 to 3 edge because that was a transitive edge. So what I mean by that is there is a 1 to 2 and a 2 to 3. 1 to 3 is shown because I can go from 1 to 2 and 2 to 3. And since we know that the relation is transitive, we know we can go from 1 to 3 without drawing it. So this is the Hasse diagram for this relation. We don't draw them in as arrows because we just want as few marks on the page as possible when we draw a Hasse diagram. And we assume they go up for a Hasse diagram. Okay, so we looked at one other relation before that we drew a Hasse diagram for, which was the subset relation on the power set of a set. So the power set of the set 1, 2, 3, 4 has the empty set, the set containing 1, the set containing 2, the set containing 3, the set containing 4, then all the pairs, then all the triples, and then the quadruples. Now, if I think about all of those, is there any of those that doesn't have anything else as a subset of it? The empty set. So we know that the empty set is going to go on the bottom. And then the next biggest things that we have are the one-element subsets, right? And the empty set is a subset of each of those, so I'm going to draw a line to them because it is a subset. And then we put the pairs on the next level because if we did more than pairs, then the pairs would be subsets of the triples. So we have to put the triples on a higher level than the pairs. And I haven't given myself enough room here, so I'm going to start over here. Oh, well, I didn't need that as much. It was supposed to be a lot prettier than that. So 1 is a subset of 1, 2, and 2 is a subset of 1, 2. And so on. So each of these should be a subset of 3 things. Oops, that was not a right one. Sorry about that. And then we have all the triples. There's going to be the same number of triples as there are pairs. Why is that? So this one is, out of the 4 elements, choose none of them. So actually there's 4. I was wrong. It's not the same number. It's the same number of ones. So we're going to have 4 of those. And the number we have at the top is C44, which is just 1. So that is obviously a superset of all of those. There we go. So this is a Hasse diagram. I don't have any edges that are jumping levels. I don't have any 2 nodes on the same level that are related to each other. All the arrows go up, so the subset relation goes up. And the original set is a partially ordered set because it's reflexive, it's anti-symmetric, and it's transitive. So we use these for partially ordered sets, and they're also called lattices. So that's another name for it, is a lattice that shows minimally all the different relationships of ways of moving around. And remember that we've looked at this example before. All of these edges are now actually in between sets that differ in size by exactly 1. So any path going up and down this will actually could be represented with bit strings, where I have a 0 for each element if it's not there, and a 1 for each element if it is there. So this would be represented by the all 4 zeros bit string. That would be a 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and so on. And so if I traverse this up and down, then I could have a path that changes by 1 bit flip every time. So I have a question. Does this have, if we ignore the fact that the edges are supposed to go up because it's a Hasse diagram. Just think of them as regular edges. Does this have, is this an Euler circuit? Is there a way to make an Euler circuit with this? No, there isn't, because all those have degree 3, right? And so do those. So it can't have an Euler path either. You're right, they do have degree 4. Okay, how about these? Those are degree 4. So we have to count the in and out. So in and out together. Okay, so there is an Euler circuit, means that we actually can find a path that goes through this that uses all the edges, that actually does bit flips of exactly 1 each time. So it doesn't visit every node exactly once, but it visits every edge exactly once. Okay, with Hasse diagrams, making them is only one part of what we have to do. The other thing we want to do with a Hasse diagram is to be able to tell, we want to characterize it. So we have a few things we want to know. So we want to know, for example, is there a maximum and is there a minimum? So let's look back at this one, at this Hasse diagram. Do you think there's a maximum? So the maximum is the highest element in the diagram that doesn't go anywhere else. And all of the other nodes have to be able to get to it. So does this have a maximum? Yes. So 1, 2, 3, 4 is a maximum, and all the other nodes can get to it somehow by going up. Does it have a minimum? Same thing. Lowest node that it can reach all of the elements. Yes, the empty set is a minimum. So this one has both. And so does our other example that we did. Our other example of 1, 2, 3 in a line. That has a maximum 3 and a minimum 1. By the way, don't be tricked by the largest number having to be the maximum and the smallest number having to be the minimum. So the labels on these nodes have nothing to do. So the maximum and minimum is asking where something is in the Hasse diagram. Yes? Yes, these are fully ordered sets. Right? So they're not partial orders, these are full orders. So if there is a maximum and a minimum, then it's a well-ordered set. But there are well-ordered sets that don't have any maximum or minimum, like the numbers, the countable numbers. Right? So those are well-ordered, but they don't have a max or a min. Okay, so maximum is, so no edges are leaving, and it's reachable from all other nodes. These are pretty easy, so maximum and minimum are easy to find. However, some Hasse diagrams can look like mountain ranges. So if you think about a mountain range, is there a maximum in a mountain range? If you use this definition, that's reachable from all the other points without going down? No. So a lot of Hasse diagrams do look like something like this. And in that case, there is no maximum because I can't reach A, which would be a potential maximum, right? But I can't reach it from E or F. And I also can't reach it from C, because in the Hasse diagram, I'm only allowed to go up, because the arrows actually just go up. So we have another property that's called maximal. So that's just like reaching the top of a mountain. It might not be a maximum. So maximal is an adjective and maximum is a noun. So there's only one maximum for a Hasse diagram, but there can be lots of maximal nodes. So maximal means I can't go up from there. So there's nothing greater than that. So in this node, A, C, E, and F are all maximal because we can't go up without going back down. And minimal is like that too, except I can't go down without going up. So E, so we draw circles for maximal, we're going to draw squares for minimal. By the way, I might change that for a test, so make sure you read the directions. So E and F are minimal. D is also minimal. Is C minimal? No, because I can go down to D, and B's not minimal, and A's not minimal. So if I have more than one minimal element, I can't have a minimum. And if I have more than one maximal element, I can't have a maximum. So one other way to tell is if you have a maximum is if there are any maximal elements. If there's only one, there's a maximum. And if there's more than one, there does not exist a maximum. And minimal, if you have more than one minimal element, you can't have a minimum. It doesn't exist. So that's it for today. And we will see you on Tuesday. Have a good Thanksgiving.